Alright guys, welcome back to part 2. So if you remember, we just finished using a model to make future predictions for the dependent variable. Okay? This last example, what we did was we just referred to the rate, okay, and then we used that along with the expected number of hours worked to make a prediction on the total pay, okay? And so we're gradually going to expand that. There's one other component that we're going to take into consideration. And this is what we call a linear function, okay? The value of y depends on x, and that value of y also depends on this rate, this rate of change, to be either positive or negative. Okay, so let's look at this next example. So distance traveled, okay? So the following situation involves the rate of change that is constant, and all of these involve rates of change that are constant. That's what gives us that linearity, okay? If you remember the section on linear versus exponential growth or decay, with exponential growth or decay, the rate of change is not constant. And that's why you get those exponential curves, okay, that get steeper and steeper and steeper. But anyway, it says, write a statement that describes how one variable changes with respect to the other. Give the rate of change numerically with units and use the rate of change rule to answer any questions, okay? So this says you run along the path at a constant speed of 2.4 miles per hour. How far do you travel in 1.8 hours or in 3.4 hours? Well, what's happening here, guys, is the distance that you've traveled or that you've run is dependent upon the time that you've spent running. Okay, that makes sense. Actually, you can think about it like this. Distance is equal to rate times time. Okay? Or in other words, time is our independent variable, and distance is our dependent variable, and then the rate is the same as the slope. Okay, so the rate in this particular example is this right here. It's the speed. Okay, 2.4 miles per hour. So the total distance traveled is going to be equal to 2.4 miles per hour times the number of hours, okay? So we're going to evaluate this for two different values of time, or for x, how do you want to look at it. The first thing, I'll plug in 1.8 hours, okay, so the hours divide out, and you multiply 2.8 times, or excuse me, 2.4 times 1.8, and we're going to get, oops, not sure what I was doing there. Oh, had a function from another class in there. Here we go. And we get 4.34, okay? 4.3, did I say 4? 4.32. 4.32 miles traveled, okay? So the units hours cancel, and you're just left with miles. And again, remember, it's really just this same equation that we're using, okay? Except, sometimes the variables that we use for our dependent and independent variable are tailored to the specific problem. So, I could rewrite this as D is equal to M times T. So capital D for distance and then lowercase t to represent time. And then some people will even use like an R for the rate instead of, but anyway. Alright, well, let's do this again to make another prediction. So the rate is constant, so it's still 2.4 miles per hour times a different value for our independent variable, 3.4 hours. And again, those units hours cancel, and we're just going to be left with miles. And we'll see what 2.4 times 3.4 is, and this is 8.16 miles traveled. Okay. Alright, so again, guys, it's just the rate times the value for the independent variable, and that'll give you a prediction for the dependent variable. Okay. Now think about this. We're going to add one extra component to this. What if we were trying to see, the total distance traveled, given that we had already traveled a certain distance? So let's say we'd already traveled 5 miles, and then we want to see what our total distance is if we travel 1.8 more hours, okay, or 3.4 more hours. Well, what you would do is figure out how far you're going to travel in 1.8 or 3.4 hours, and then add to that the distance that you've already traveled. Okay, so that brings in this last component that we're going to talk about. Okay, so from the previous example, consider that you'd already walked 3 miles and wanted to know the total distance after 4 hours. Okay, so that previous function wouldn't be sufficient. You need to add the 3 miles that you already have traveled. So you're going to end up with another equation that has this form. So instead of y equals m times x, you're going to have plus some constant. Okay, in algebra, we use b to designate that constant. So the constant in this case will be the distance that you've already traveled. And this is formalized down here below. If you look, the value of the dependent variable, so like our y, is going to be equal to the initial value. They put it first, and then plus the rate of change times the value for our independent variable. But in algebra books, guys, the mx part comes first, and then the plus b part comes second. Okay. So think about b as being the quantity with which you're already starting. So let's say you were going to deposit, you were going to start saving, but you had already saved a certain amount. Okay, so that the amount that you already had saved, or that you already had, would sort of be like your b. Alright, so let's look back at this example. So we need to add the 3 miles that we've already traveled. Okay. So the process is going to be very similar. The total distance is still going to be equal to the rate, which is 2.4 miles per hour, times the time. So if we're talking about 4 hours, okay, plus the distance that we had already traveled, which is 3 miles. And so these units, hours, still cancel out. You're going to multiply 2.4 times 4. That's going to give you the number of miles that you cover in those 4 hours, plus the 3 miles that you've already covered. Okay. 2.4 times 4, I believe, is 9.6 miles. Plus that constant, the 3 miles that you've already covered, and this is going to give you a total of, I believe, 12.6 miles. Okay, so that would be the total distance. So we're bringing in this other value, okay, this initial value. Alright. So an algebraic equation for a line. Well, I've already given you that, basically. In these symbols, we can express that equation like this, okay, where n represents the rate of change. I'm going to write this in here. And I'll just put rate. And b represents the initial value. Okay. And of course, x represents your independent variable, whatever that is, and y represents your dependent variable, or typically your final value. Okay. We actually use this equation. No, we didn't. But anyway, let's continue. Okay, so when we have an equation in this form, this is called slope-intercept form of an equation. Meaning, when you have an equation written like this, you can easily graph this. Okay? Now, when you graph any of these linear equations, they're always going to be lines. Okay? They're going to be lines on a Cartesian coordinate system like this, but where are those lines going to be, and how can we figure that out? Well, I refer to this, the form of this equation as the slope-intercept form, because the slope, which is the same as the rate, is given to you, and the y-intercept is given to you as well, or the initial value. Okay, so let's look at an example here. So for example, this equation, y equals 4x minus 4. So the rate of change is 4, or 4 over 1, in other words. And the initial value, b, is negative 4. So when you go to graph an equation like this, the initial value, negative 4 in this case, that's where your line would start or would cross the y-axis. Okay? So whenever your value for x is 0, then your value for y is negative 4. Okay? So you get this point right here. And then you use the slope, which is 4, or 4 over 1. Think about 4, which is the same as 4 over 1. Think about the rise over 1 again. Okay? So once you know what your y-intercept is, I'll finish writing the rest of this. Okay. Once you know that this line is going to cross the y-axis at negative 4, you put a point there. And then the way you graph this equation, or graph a line that represents this linear relationship between x and y, you need another point. You need 2 points for a line. Okay? And so once you've got your y-intercept, the way you get that second point is you let the slope direct you. The slope is kind of like the directions on where to go, how to rise and run. Okay? So if I'm sitting here at negative 4 on my y-axis, I'm going to rise 4, so bring me up here, and I'm going to run to the right one place, and that's where I put the point. Okay? And so when you connect those two dots, you're going to get a line that looks just like this. It's going uphill because the slope is positive. If the slope is negative, the line's going to be going downhill. Okay? Let me say a couple things. So if the slope is positive, you will rise. If the slope is negative, you will fall. But you will always run to the right. Okay? Alright, now back to this one. In the context of this problem, your y-intercept would start at 3. That would be your first point on the y-axis. And then your line would have a slope of 2.4. Okay? So it would rise 2.4 and it would run 1. Because that's the rate of change. And that line, if you were to graph it from those 2 points, that line would show you how x is related to y, or in other words, how time is related to distance, or distance depends on time. And you can use that as a model to make predictions. Alright. We can read this here if you want. I'm going to keep going. So what happens when the slope varies? Well, we've talked about this. Okay. So if m, which represents the slope or the rate of change, is greater than 0, that means that it's positive. And so you get a line like this one in red. It's going uphill. Because that just means for increases in your value of x, you get increases in your dependent variable, and that causes the line to go uphill. let's see, a negative slope, or in other words, when m, or the rate of change, is less than 0, you may get a line that looks like this one in black. Okay? And what that means is that for an increase in the value for x, you actually get a decrease in the value of y. And so that causes this line to fall. Think about the price of pineapples and the number of pineapples sold, right? As you increase the price, the number of pineapples that you can sell actually falls. And I think it falls by $10 for each. No, it falls by 10 pineapples for each dollar increase in the price. And then, guys, it is possible to have a slope of 0. This would be if you had something that had no rate of change, okay? You would end up with a line with a slope of 0, and that's a horizontal line, okay? I don't know that we're actually going to see that or not, but... And then what happens when we vary the intercept? Or in other words, when we vary that value of b, okay? So up here, if this is our standard form for our linear equation, we can vary the values of m, and that'll give us either a line that's going uphill or downhill. What happens when we vary the values of b, or the initial value? Well, that just moves the line up or down, okay, depending on what that initial value is. So here's some different examples. When b is greater than 0, so when b is positive, your line is going to cross the y-axis at whatever that positive number is. When b is 0, or in other words, when there is no b, your line crosses right here at the origin in the center. And that's how those initial equations that we were working with, that's what would have happened with them. Because they didn't have a constant out here, they would have crossed the y-axis right here at 0. Because there was no initial value. There was 0 initial value, essentially. And then lastly, if b is less than 0 or negative, then you're going to have a line that crosses the y-axis at whatever that negative value for b is. Okay. So the value for m, or the slope, the rate of change, that causes the steepness to change. And then the value of b causes your line to shift up or down, depending on what that initial value is. Okay. Alright, so let's try graphing one of these. So it says find the slope and the y-intercept of the following function / line, and then graph it. Okay. So you can see that this is written in that form, y equals mx plus b. You've probably heard this before, or remember it, maybe from high school. So m in this case is 3. Okay, so the slope is 3. But I'm going to express that as a fraction, 3 over 1. Okay, because remember, we're going to interpret this as rise over 1. And then the value of b is negative 2. Okay? So my y-intercept is going to be the ordered pair 0, negative 2. Okay, the x-coordinate has to be 0. That's what puts it on the y-axis. Any point on the y-axis will have an x-coordinate of 0. Okay? So the y-intercept itself is an actual ordered pair. It's a point. Now to graph this, or actually let me say the slope is 3, 4, 3 over 1, and then the y-intercept is the point 0, negative 2. Okay. So to actually graph this, you're going to plot your y-intercept first. You're going to put a point at negative 2 on the y-axis, because that's your initial value. And then you're going to use the slope, rise over 1, to tell you where to go from your initial point. So you're going to rise 3 and you're going to run 1. So if I go up 3, right here, and if I run to the right 1, I end up with this point right here. Okay. is my line. Okay, and this line has a slope of 3. And this line, would represent anything that has an initial value of -2 and has a rate of change of 3 units per whatever. Okay. We don't know what x and y actually represent. It's just an abstract. This is what you would see more in your algebra courses. Alright, let's try another one. Find the slope and the y-intercept of the following function/line and then graph it. So this one's the same way. We can see that our slope is -4, or -4 over 1. We can see that b is 3, okay? So the slope is -4 over 1, or just -4. Remember, this refers to rise over run. In this case, it's going to actually fall, though. And then the y-intercept is going to be the ordered pair 0, 3. Okay. So when we go to graph it, we're going to plot our first point at 3 on the y-axis, so right here. And then from this point, we're going to let the slope tell us where to go. So we're not going to rise, we're actually going to fall 4. So if I fall 4, 1, 2, 3, 4, and then I run 1 to the right, that puts me right here. And that's my second point. Okay. And so if I connect those points, I didn't do a great job of it, but this is roughly what your line is going to look like. Okay. Well, I think that, let's see. We've got a couple left we need to do. So let's look at this example. So here we have an example in which we can use a linear function to model what's happening here. The price of a particular model of car is $18,000 today, and then it rises with time at a constant rate of $900 per year. Okay? So the rate, or the slope in other words, is this right here, $900 per year. And this is actually your initial value, okay? Because that's what the car costs today. Because what we're trying to do is model the cost of this car into the future. So the initial cost, or B, in other words, is $18,000, but the price is going to rise by $900 per year. So we want to figure out how much will the new car cost in 3.5 years. Okay. All right. So I know that my rate is $900 per year, so I'm going to plug that in for N. $900 per year times X plus the initial cost, which is $18,000. Okay. And all of this will give us our future price, or Y in other words. Okay. But I need to plug the 9.5 in for X. Okay. That's the value of our independent variable. In a lot of these problems, guys, time will be your independent variable, because lots of things depend on time, right? So I'll plug in here 3.5 years, and so the units cancel years, so we'll multiply 900 times 3.5, and so this is how much the price will rise in 3.5 years. But we need to add to this what the car cost initially to see what its final cost is going to be in 3 years. When I add that $18,000 to it, I get $21,150. Okay. So all of this equals $21,150. Okay, so that's the price of the car after 3 years. You can see how we created this model. And if we, if the rate at which the price changed stayed constant, then we could predict what the price of this car is going to be in 10 years, okay, in 7 years, etc. I'm assuming the price is rising due to inflation. That would be my guess. Okay, but anyway. Alright, let's do one more example here. There is one last example, but I'll let you read through it. I'm not going to go over it. It's a good one, though. Okay. So what if, in all the previous examples, we've been given the rate of change. Well, there were a couple in which we weren't given the rate of change. We were given two data pairs or two ordered pairs, and we could calculate the rate of change, right? Because it was the difference in the dependent variable divided by the difference in the independent variable, or in other words, this right here, correct? The change in your y divided by the change in your x. Okay? And so, if you want to create a linear model, but you only have two data points, and the first thing you do is you use these two data points to find the rate of change. And then once you know the rate of change, then you need to figure out, you need to substitute numerical values for x and y to be able to figure out the value of b. Because b is the initial value. Okay? And once you know the value of b, then you've got your model. Okay? So let's try this. Well, we're actually not even going to have to do that because this example, it gives us the rate of change. Okay. All right, so all of you culinary students in my class should hopefully appreciate this, because I know in the culinary they do some fermentation, okay, alcoholic fermentation. And I myself have actually done a fair amount of this. I've brewed my own beer, my own wine. Anyway, it's a fun and interesting process, okay, especially if you like to consume a little alcohol. Alright, so this says that the amount of sugar in a fermenting batch of beer decreases with time at a rate of 0.1 grams per day. So this is your rate right here. And notice it's decreasing, okay, the amount of sugar. Because what happens when you brew beer or wine or any sort of alcoholic beverage, you utilize yeast, and you have to feed the yeast, typically sugar. Okay, now it doesn't have to be, it can be sugar from grapes, sugar that's inherent in grapes, or sugar that's inherent in other fruits, because there's fruit wines. It can be sugars or complex sugars that are in grains, okay, for beer, for example. And that's what the yeast eats. So as the yeast is consuming the sugar, part of the process is that, or one of the byproducts in fermentation, is that the yeast will give off carbon dioxide, which creates the bubbling, and also, if you do everything naturally, it can create the carbonation. But nobody except like maybe DIY brewers would actually create carbonation strictly from the yeast. But a second byproduct that the yeast give off is ethanol, okay, which is the alcohol that most people use to feel better, okay? Just put it that way, or to relieve stress, or maybe they just like the taste of it. But anyway, so this is going to be a negative, okay? Let me plug this in. And furthermore, it says we're starting with an initial amount of 5 grams of sugar. Okay, so we want to write a function that shows how the amount of sugar varies with time. Okay, so the amount of sugar depends on time. The sugar content will be decreasing as time increases in the fermentation process. So let's think about our standard equation here. Okay, so we know the value of m, we know the rate. It's negative 0.1 grams per day times x. So x represents the number of days. Y will represent the amount of sugar that's left, plus the initial amount of sugar that's in there, which is 5 grams. Okay. So this is our equation right here. This is our model. Okay. So if we wanted to see how much sugar is left after 2 days or 3 days or 4 days, we plug those values in for x, evaluate this, and this would tell us. But the question is, when is the sugar gone? So it's not how much sugar is left after so many days. It's when is the sugar at 0? Okay? So when they say when is the sugar gone, they're implicitly saying when will y have a value of 0, because y represents the sugar content. Okay? So this one's a little different. So when is there 0 grams of sugar? Okay? So in other words, instead of plugging a value in for x and evaluating this to see what that corresponding value of y is, now we're plugging a value in for the dependent variable, and we're going to try to figure out what's the value for that independent variable. In other words, how many days will it take for all of the sugar to have completely fermented? Alright, so I'm going to recopy the rest of this, grams per day, times x plus 5 grams. You could probably take the units off while you're trying to work this out, because guys, what you have to do here, this involves a little bit of algebra. What you have to do is solve this equation for x. Okay? And so you need to eliminate the 5 on the right-hand side. And so you're basically doing the opposite. So instead of adding 5 grams, you're going to subtract 5 grams. So if you remember any of your chemistry, or not chemistry, but any of your algebra, whatever you do to one side of an equation, you need to do it to the other side. Okay? So 5 minus 5 is 0, so we cross that out. This leaves us with negative 0.1 times x. I'm going to forget about the units for a second. And this is equal to, now I need to subtract 5 from the left-hand side. Well, 0 minus 5 is actually a negative 5. Okay. And so we need to isolate for x to be able to answer this question. So the x is getting multiplied by this negative decimal. So you do the opposite. You're going to divide both sides by that negative decimal. And when you divide the right-hand side, anything divided by itself is 1. Or, if you think back to the unit analysis that we did earlier in chapter 2, these divide out, or they cancel. And so we'll just be left with x is equal to, and now what I need to do is divide the negative 5 by the negative 0.1. So if you do this in your calculator, guys, a negative divided by a negative is a positive, and that will actually go 50 times. Okay? So x has a value of 50 days, because x represents the number of days, and y represents the amount of sugar in grams. Okay? So after 50 days, all of the sugar will have been fermented. Or in other words, you will have maximized the alcohol content. Okay? Now, I do want to point out that in processes like these, the rate of change, or the rate of fermentation, it actually changes. It actually slows down the more alcohol. The more sugar that gets converted to alcohol, that creates an adverse environment for the bacteria. And so consequently, they're no longer able to ferment at the same rate. Okay, so this model here is a bit of a simplification. I just want to point that out to you. But anyway, and then the last one here, guys, you can read through that if you want. This would be an example of coming up with a model when you're given two data points. Okay, coming up with a rate of change, and then figuring out what your constant is, and coming up with a linear model right here. And you'll see if you read through this example that a linear model, the linear model is right here in red, but the actual, I think this is consumption of oil, was more like this. It was more exponential, okay? So, there's not a whole lot of processes in life that you can model that are actually linear, okay? Most of them are exponential in nature. We could model them linearly for a short amount of time, but over long periods of time, you need more like an exponential model to more accurately model the process. But anyway, I think I've talked enough. Okay? All right, so this is it, guys. This is the last part of the material for this course. So the only other thing that I need to do is record a review for your last test over chapters 7, 8, and 9, and then I'll also need to record a review for the final. Okay, so I'll get those done